Yeah, okay. So, this is about EEPROMs and tears, but we made a little fun about it, so we call it for tears. It works for us non-native English speakers, but yeah, the British people in the room always dislikes it. So who am I? I'm Iceman, or you rather know me as Iceman if you've been into the Proxmark community, where I've been an administrator and forum manager for some good old 7 years. I have a life outside of this. I do this as a hobby, as a funny thing to do, and I have been contributing to the source code very much because I'm a code monkey, and my friend here is the chip monkey. We're the next generation, Adam. And we also did a little device, but we're going to talk more a little bit later on. And I'm also a co-trainer for Red Team Alliance, where we do a practical RFID packs, attack and defense. So, quick over to you.
Oops, not too fast. Too fast. I'm Philippe Teuwen, do gogs on the internet, but don't try to say the word, just write it, it's fine. I'm team leader of the cryptography embedded security team at QuartzLab, and you may know me for some other, like white box attack papers or open source projects. And since a couple of years, I am mostly a contributor to Proxmark and maintaining the Discord forum with Iceman. Did a lot of trainings on the topic as well. And by the way, the drawing up. How does it come that we are all working together and doing funny research? It's thanks to the Null Content 19 event, so thank Antrick a lot for things happening now today here. It's all thanks to you. So, and you
we all look a little bit younger than
usual suspect on that picture.
Isn't it fancy?
You want it back, or you want to comment the picture?
No.
Okay. So yeah, what's a physical tearing? Tearing is a technical term when someone wants to badge his RFID tag on a reader, and on the metro it goes away a bit too fast. Maybe the reader was busy writing on your tag, and when you take it away, well, the power supply of the card drops with the field, and maybe you risk to corrupt the memory. So that's something quite usual that they have to deal with, and most RFID tags nowadays, they have to support it because that's stuff that can happen in the life. So we will explore a bit more in detail this type of event, what we can do with that, what is the EEPROM physics phenomena behind it, and understanding allow to get better control on what's really happening. And then we will check what kind of security feature could be defeated on that. And we will show 4 different examples of RFID tags and features that we could play with. And all that was done with support of some tools that we made, open source and now available on the Proxmark repository. So, yeah, how to tear the tag when we want to do that in terms of research. We don't do a little robot that will take the card away. There is much simpler. We just cut the power of the reader at some precise timing. And because the way RFID is done, when you cut power on the reader, you cut the power of the tag. And that's something Iceman can cover with as well the tools we're using.
Yeah. For our purposes and tests, we were using the Proxmark out of A4. We will talk a little bit more about Proxmarks about later. But if you don't know anything about RFID, you need to know it's about magnetic coupling to transfer power to the card or the tag, which you see down below here. You can see the concept of this as the magnetic flux. You're building up a field, a near field of this antenna that's powering it on. So when we do tearing or tearings, we actually cut the power, and that magnetic flux strips away very fast. That goes away instantly. But what's left is in the coil, in the tag and capacitors on the tag. That makes, this attacks a little bit unprecise in a sense. It's like it lingers on. But basically, yes, it's a loop antennas, both for LF and HF. So we do it with a Proxmark. 2004 was a guy called Jonathan Vestius. He's an engineer in California, and he was very curious about something that the governor there said, very cheap, so very secure, so we can't clone them or do anything with that. So being an engineer as he did, he started to think about it and tinker with it and start building a device. This is what's called the Proxmark. That is the one you see up here to the left. That's the first iteration of it. And you see, like everything else, he went over to some more iterations of it. This is his Proxmark 2. And in the end, 2008, he also made a Proxmark version 3, which is actually, until this day, the same hardware, but we still use the same basic schematics and schemas about it. So from 2010, this green PCB board came out, but it's... before that, you had to hand solder it yourself and make all this stuff, because he made open source and open hardware, but he didn't make a product out of it. He's since long gone, but what you see after this was several iterations of Proxmarks coming out. And we were using, or I was involved with it, in making the RDV4, which you see here. Funny thing with this one is that this little piece here is the circuitry. The rest is the dual antennas. Here is this, that's not the proper size, this is much bigger. This has batteries and all that stuff you want to add it on, so it's proper. But it's gone the whole way from there to now. But remember, we're all using the same software. So this runs the same stuff as that one. So if you have an older one, you can still run and do all the things you do today. I'm not sure if it's some older attackers or Proxmarkers here, if you ever had used one. Has anyone here used a Proxmark before? Holy shit.
Cool. Wow.
That's amazing. Oh, that's great. Let's get on with it. Perfect. That's not your software, I know. Anyway, let's see. We need to go to the terminal. So we are like, we're going to have this, pleasing the demo gods today. We're going to do live demonstrations about things. So we hope it goes well, and keep your fingers crossed for us. And we need to turn our heads to look when we type, so please take that in consideration as well, and we go from there. But basically what's happening is, if you take a simple card, let's say like MIFARE Ultralight, it's a simple tag with a little piece of memory. We choose a user memory address called block 4, which is all available to read, and we write to it. We set it to a value called FFFFFs. And if you interrupt that, you launch a second write and interrupt it, you shut down the field after some seconds or microseconds. In the, yeah, I can do this as well. If you shut it down, we like observe what happens, and then just like read back the memory points. And if something good happened, what we're interested in, we don't have to repeat, but normally it doesn't, because that's the whole thing, is finding the right timings and figure out what's going on. So you have to go back to set up there, initial value, initial state that you want to go from, and then you try to understand the rest of it. Let's demonstrate like this. So here, as I said before, we did the write FFFs. We trigger the second one with a tearing at 200 microseconds, and afterwards we do a read and see, nothing happened. We increased the timing, nothing happened. We did the write, we interrupted, and something happened when we read it. What was going on? This goes on all the way down to about 200, and then you see in the next one, 2,400 microseconds later, that you see the new value. So what we see up here is the old value, this is the erased value, and this is the newly written value. So we take that and start thinking about it. What can we do with that? Can't do very much, actually. Yes, we can. Okay, so with that in mind, knowing the process of what happens in EEPROM during these attacks, what do we need to know? We need to have something that involves writing to EEPROM with an erase or a write command. We need to have something that we can trigger, that we can control, and we don't influence the output of it. So it's not like a normal write to a normal user memory, because that would be useless, because if you want to write all zeros, we could have done that. But if we can't control the output, that makes a whole deep difference. Yeah, so the first attack we will demonstrate is on
Russian card, which is a clone of a MIFARE Ultralight, which was used some years ago in the Moscow metropolitan. And it has a layout pretty much similar to the MIFARE Ultralight. So this is a memory layout you see there, and there are here OTPs. OTPs are one-time programmable bits, which means once you flip a bit to 1, you can never go back to 0. So it's used, for example, in transportation because you can mark journeys on the same card, and you burn a bit every time someone travels. So if you have 32 bits, you can validate 32 travels, and then that's over. So this one has the characteristics Iceman was looking for, because you can write to OTP, but you can't control fully the result. If you want to get it 0, you can't get it 0 if there are already ones in the way. So, for example, here, if the OTP has a value 1, 2, 3, 4, 5, 6, say 7, 8, and you want to write all zeros and a 1, what happens is that the card will read the current OTP value, will do a logical OR, so it can only set bits, and say, okay, that will give the last value, okay, thank you, with a 9, and it will write that value to the OTP memory. So if you read it back, you won't read the value you wrote, but you will read the result of the logical OR between these two values. Except that in that specific card, to trigger, to do the write operation, they do a regular EEPROM write involving the erase that you saw first when we tried on the other ultralights. So if you want to attack such a card, it's pretty easy. What would you do? With tear off, you tear just after the erase. And then that's it. You get zeros. That's not an attack from us. It's an attack from Nawal Guzoli and Philippe Teuwen that published it in their student thesis last year. But still, Iceman can make a demo out of it.
Let's see about that. But you knew about this attack long before. You had it in your trainings, didn't you? Philippe does trainings. Right. It takes a little bit of fiddling here with a camera and everything to set it up. All right, great.
You're set up. Give me.
All right, let's... Oh, Jesus Christ. I'm going to get a headache from this. And let's see.
I can spell what you type.
Thank you very much. As you see in the camera, that's a Proxmark 4 RV4. Proxmark 3 RV4. Yeah?
So I will give you the notes.
Yeah, thank you. Would be nice. Am I in there? No?
You're here, so you can copy and
okay.
there.
All right, great. So we're just going to go over there. Where am I? Yeah, okay, here. Okay, great. Yeah, hello. So, great. Inside the Proxmark client, it's a little bit different. If you ever used it, you know, it's been a little bit complicated over the years, but with contributions, it's become a little bit easier. I'm talking a little bit faster because I want to get over this section quite fast. Normally, you just type in help. Oops, no, that's wrong. Enter. There you go. And you see something nice, outputs explaining what it is. I also briefly say, here's the commands. And here's a description of it. However, not all things are commands on the Proxmark client. We have a hint saying, if you see this angle bracket, it's a category of commands. So here would be without, that would be a command that you run, and this would be a category that you go into. And that's what we want to demonstrate right now. So for high frequency, you type in HF and you press enter, and you will see the high frequency commands. It's a little bit large, so it's hard to say. And if I would put on a little card onto here, micron over Proxmark. When it comes to 14A, you need to have some distance. So like usually put on this nicely Bluetooth Billy Blue Shark thing. And then you can type in HF search. And I type like a crazy person today. Here we go. the Proxmark identifies and shows you the anti-collision of a tag and gives you a hint and note that under HF MFU info, you will see that this tag has some more information. Which is the interesting part. You see it's an ultralight. It's identified as Micron from Russia by that little value. And this is what we're interested in. This is the 4 zeros here. This is an unset OTP. And our purpose is to demonstrate what happens now. Let's see. God, this is bad. Oh. It's a different keyboard as well, so it's... Jesus Christ. Sorry about that. Wrong. Lots of spaces here. Oh, free, thank you.
No, it says it didn't answer.
There you go. That's reading the block 3. Block 3 was, as Philippe was showing before, is the OTP value. So this is what we're looking at right now. If we were to type write commands, right, block 3, data.
Space.
Oh, it's lots of spaces here, Trace.
No.
All right, cool. So we now set some blocks or OTP bits. Or if you like to look at the info again, you can definitely see here that the OTP has been set. So now we will show you that the bit flipped goes one way, not the other way.
Okay.
What? We tried to make a write with all zeros to block 3. It says that the command executed, but it wasn't successful in that sense. And as you look at the output of MF info, you see it is still the same values. Oops. Let's see. What? Let's try and set some values. Again, I go upper because I can easily don't have to retype things. And as you see down here again, you can set flip values up, but you can't erase them. All right, so that's the setup. Something we can control, but we can't control fully. Wow. Jesus Christ, this is hard. HF MFU. Oop. For this particular attack, we implemented a command, or an OWL implemented a command, so you will find it, oops, up there. It says OTP tier, there. And when you have it,
You can complete it, copy paste it.
okay. Oops.
Ah, sorry.
No problem. I will remove this. This is how you call the command. We're not going to go into exactly all the details, but you can manually set do increment by 100s, start at 100 microseconds, and at 2500 microseconds, and use the values 11223344. We run an attack, and you see that the tearing triggers, and you see something happens, and you see, remember how we presented the slide where you saw the values happen and not happen? Here is the raise to zeros. We triggered after 3, 4, 500 microseconds, all the way down to 2000 microseconds. And then you see the new formally written OTP values. If you look at that, that's cool, that's interesting. We can run HMFU info again. Whoop. You see that the FF that we had here before has now been overwritten. Now that's fun, but not really super fun. Yeah, I do it. Just jumping to other sides. Yeah.
because it's Control-Shift, not copy.
Okay. All right. Let's set it all to zeros, and we say that we want to actually instead start a block, target block 3, but we want the matching values to be zeros instead of trying to say the range and everything. And it goes quite fast because this is a really crappy implementation of our OTP. So actually 2 triggers and that's it. The OTP is reset. And now you have a whole complete untouched OTP. Now, why is this interesting? Now, this is interesting because MIFARE or microns was used in the subway of Moscow, meaning that they flipped for each transport we did, they flipped a bit, saying that you have 10 times, 9 times, 8 times. But with this, you could just go home, and at the end of the day, do your trips, go home, reset the thing, and you have a brand new card working the next day. Time for applause.
That's yours.
That's mine. Oh, that worked. Oh, perfect.
Just go up. I think it's me. Okay, that was the kind of textbook cases here, where we just interrupt at any position over there. But now we're interested to look more in detail what happens, like, oh, shit. Somewhere around these values when it goes from F's to zeros, and around these values when it goes from 0 to F. And we want to explore a little bit more detail in these areas. So we do just the same tiering, but with other timings. So, and here, if we zoom on that area between the 400 and the 600, we see that it's around 500 something. We see progressive bit flips. And there are a few interesting things to see. First, all events are independent because we always start from a fresh normal write that goes to FF normally before we do the second tearing. And still, we see that some bits are erased first almost all the time, and some bits are harder to flip and are flipped last. This is due to the manufacturing process to generate the transistors, making the EEPROM, because there are some dopants, it's a gas, and so locally you may have small differences between the transistor, and these small differences will change a bit the physics of the transistor and the speed at which it will flip. And it will be different for another card, and it will be different for another memory of the card. And you can even use it like to fingerprint physically a card if you want. If some of you were used of SRAM physical unclonable function, you can play kind of similar things with an EEPROM. If we look at the write phase from 0 to F, there is also an area there around the zone 300 something. It's a bit quicker than the erase on that card, but you see similar effect and similar bias between the different tags. So you may think that internally the EEPROM is like a little switch, and if you tear off, some have had time to flip and some didn't have time to flip at all. Physically, it's not exactly correct, and it's not good enough then to think about a smarter attack on that. So for that, I have to explain a bit how EEPROM transistor works internally. I won't go too much into the detail. Just remember that there is, like here in red, a floating gate, which is like a conductive element, which is trapped in some insulator. So electrons can't move in and out. Still, if you apply a large voltage bias between source and the gate, you can drag electrons into the floating gate and out of the floating gate. So you can charge electrons and discharge electrons. And if you measure the physics of the transistor, it will vary, and that's how you can read a value stored in the EEPROM. So better analogy is to look at not as a switch, but as an analog value that can go from 0 to 100%. And if you tear an erase a bit too soon, you will empty a little bit each transistor, and remember each transistor has its own rate. So you get something like that. If you read the value, the readout will be something like, look at the 50% threshold, what happens, and it looks like nothing happened. You still get FFs. But internally, the value is decreased. So if you go on, then you will see the first bit flips, and so it's a very progressive thing, analog things going on there that is discretized when you read it out. And sometimes you can have even funny stuff happening, like if I go on the third, up on that one, yeah. It's just a border, and the readout has also some randomness in this physics. So if you repeat several times, sometimes you will read that weak bit as a 1, sometimes as a 0. The EEPROM storage didn't change, but the way it's read out may vary from time to time. It may vary with different factors we will cover, so that we can even control a little bit the way it will be read. So if we take back our previous experiment, and we don't reset to FF every time, so now I write only once FF, and then I'll only do tearing, and I would choose much quicker timings. Look here, the timings were at 500 something. Now I do just a first tearing to be close to the middle, but still some gap to meet, and then I do a very quick tear to always remove just a little bit of the electrons, and like 20 times here nothing happened, and then you start seeing the flipping bits. So by that way, we can control even more precisely all the intermediate states of an erase. We can't control
does that make sense?
Which flip.
Does that make sense to you, how the electrons goes out and slowly we can gradually see bit flips in the reading out of it? Okay, good. So now we've already a few techniques to control what's going on when an EEPROM operation, erase or write, occurs. We saw that we can just tear between the operations, easy. We can tear during the erase or during the write operation, and we saw that there is some statistical bias between the different bits. We can use it even for fingerprinting, as I said. And we saw this progressive tearing to get even finer control on it. We have to also watch for some effects that you necessarily don't want. The timing that you're choosing may vary with different factors that you have to take into account. The distance to the reader, if you're further away, you need a bit longer time because the card doesn't get as much power. We saw even that temperature can affect the timings. And also the content to be erased. If they are all flipped bits to once and you want to erase them, it takes a little bit more time than if there is a single bit to drag. We can also have some control on the read phase when there is a weak bit. Again, the distance can play. If we are close to the reader, we may see more 1 on this weak bit, and when we put the card a bit away, then there is more chance that it will be read as a 0. Again, because the card gets less power, and the comparator entirely will have, for the readout, will have a different level. Another effect is the time since pouring. Again, it's the same logic behind. If you pour the card and read immediately, you have more chance to see the 0 than the 1. And if you give more time for the power to settle, then the card has also more power and more chance to read a 1 at the weak bit position. And you can control both, of course. If you want to see more of 0, go far away, read fast. If you want to see a 1, come close and read a bit later once the power is settled. So we will go very quickly on second example because I think... that's mine.
No, that's mine.
Okay. Go.
You go the EM, I go the T55.
Oh, okay.
So the T5577 is like a generic LF card that can emulate many stupid LF cards, which are just an ID and no smart crypto or whatever. And it has a security feature, which is a password. You can lock the card, and you have to know the password to be able to communicate with the card. So internally, it's also just a memory. So one slot is for storing the password, and one slot is the configuration. And in that configuration block, actually, there is one single bit. Can point to that. That says if the password protection is enabled or not. And funny thing on that tag is that there is also a test mode, which is still available even in production. Test mode is normally for manufacturers to check quickly the EEPROM state, and they can flip all the EEPROM bits on ones and zeros to check that everything is working fine. So we can use that test mode even if the card is locked with a password, but okay, test mode erase the whole tag. So what to do with that? Well, actually, we can tear the test mode with a progressive tearing very slowly, just to get a few bit flips here and there. And we do that until we manage to flip the password bit in the configuration block. Once it's done, we can do whatever we want. We can write again a configuration block to set the card in a proper state that we can understand, and we can read out the password memory block. Some bit flip occurred. It's not the real password, but at least we get already some information. All the ones you see in the password that are bit that didn't flip yet, and you know that the real password contains also ones at these positions. And that card doesn't have a UID, so that means on the system, all the cards will share the same password. So you kind of destroy a tag, discover partially the password, take another tag, attack it also, get some information again on the password, do a logical OR between the results, and at the end you will break the password, have the full password, or good enough to finish it with some brute force behind. So that's the first attack. That's all what I said there. And another example that will be demoed is the EM4305.
EM4305. Electromarine, another simple. Did you understand about the T5577 attack that Philippe was talking about? Did you understand the concept of it? How we erase parts of a memory, realize that flip one bit, and then we can extract information about it by looking at other tags later on? Did that make sense to you all? Perfect. I see nodding heads. You're a very attentive crowd. I'm very happy. When it comes to another LF tags, I don't know why we choose LF tags, because we're so damn simple, I guess. There's no cryptos and stuff in. Yeah, so we did that. It turned out that we got very excited about this tearing, and we're like, let's see, this is an anonymous tag again. It's usually used for HID prox cards. The IsoProx 2 cards is based on these ones here. They have a password. That makes interesting sense, but we know that they have a read-only UID. And if you look at an EM45, E4305 tag, the memory looks like from 0 to 15, 16 blocks of 32 bits of values. The interesting part here is that you have lock bits, that's the UID. And you have 2 lock words down there. Now, these words down here are called protection locks. So protection words? Protection words. And it is actually very interesting because you see this 8 and this 2. So 1 bits here, this 16 bits here denotes which lockup here is locked. Did that make sense? I don't know. It sounded better in my head. So, writing lock configuration blocks. So the bit maps of the word we were looking at, it acts, it's kind of like an OTP because you can't clear it. Once you locked it, it's perma-locked. Interesting. And the last bit indicates which one is active. So it has 2 of these ones here, 14, 15. That 8 means that this one is active. Keep that in mind. Boop. Here you go. So, when we write these ones, we have to send a command called protect. So if you want to write and lock the first word at index 1, we send this. The reader sends the commands and the card goes like, okay, this is the active ones, looks at it, it adds the value of 1 to it, and it flips over 8, and it erases word 14. So it flips between those two states. So this is the process. Like, it's more visualizing to see it than otherwise we were guessing on the OTP on the ultralight tag. So you can more see how it works. Oops. Okay. Funny thing is, of course, this is there to, according to our own datasheet, to protect things like unwanted bit flips to 0. I.e., there I have anti-tearing countermeasures or measurements, which is even more interesting, because now we thought it was fun. What can we do with this? How about we launch and interrupt a protect command? And the idea is, can we make sure by flipping that second bit to enable things for us? How are we going to do that? Remember we were talking about the progressive flipping of bits? It all comes to mind right now. If you do that one, both protection words becomes active, but one has always priority. It's also good to know for us when we do that, which one we do, because we need to know where to start from. And
yeah, that's something you can easily test. You like lock a word and then check if it's locked or not. No, you know if it's number 14 or number 15, which takes priority.
Yeah.
And the answer is that it's 15.
Yeah. So
just test it.
The whole thing goes in a very interesting loop where we adjust the timings and deal with the kind of odd things where we have weak bits we described before, some flips what we don't want to have flipped, and then we restart from a stable situation if we fail. So we write a normal write, so we make the protection word 14 in a proper state. Oops. So this one here is actually implemented as an automated attack as well. It takes about 5 seconds to several minutes, but we have about a success rate around 85%. It's not 50% because of the bias in the flipping of weak bits. So that's why I have a little bit more success rate for it. And we shall actually just demonstrate it right now. Oops. Click. Oh, you have a password on that.
No, not that one. On this one. For tear off.
Yeah.
That's return.
Yeah, if you want to see it, it's if you can see it, it's the HID. Yeah, HID ISOProx2 cards, kind of popular in the States. Don't think they're that popular here. Or have you seen those in Europe much? Yeah? Okay. Adam nods, that's why.
Okay, can go.
Okay, boom. Let's see. I feel like a musician like this. All right, good. Well, let's go into LF. EM, and it's 4x05. Let's see what commands we have here. I will do this again. Damn, it doesn't work for me. So, unlock. There is a command called unlock. But first we want to look at the command on the data on it. So we will make a dump. Let's see if it works on the tag. All right. You see the UID lock bit is set. You see the 2 is there, and this is the active slot 14. Great. Let's go for the unlock. Yeah. If you want to see, oops, the help starts. Oh, no.
And send positive energy, so that's it. Make sure it works.
Yeah.
Just unlock it, it's good enough.
Chill, Winston. All right. Here's the timings. loops we were talking about, it is adjusted around. It should converge around 40, 60 around here. Here we go. Yeah. Triggering. Too late, too soon. All right, go up and down.
I forgot, but it's better if we put the tag a bit further away. Here, I'm not sure to get it. You can stop and we start over from a bit further away.
Let's do it again. Should be fast, I'm sorry about that. Is that better?
Try.
Okay, let's go. 4,000 demo guards, come on, give it to us.
Again. Toolbox.
I think you're too much far away, that's why.
No.
The demo gods are not happy. We should have... no kittens today. I'm so sorry. Everybody's just blindly looking.
Here you see some results. So there are some bit flips, but not the right bit. It's the 8 was flipped. And now it worked. Okay.
Okay.
Good.
Success. So, if we dump the card again, you will notice that this little baby is gone. And it's still active and has 800 or 8,000 there. Meaning that now, from a read-only UID card, we have now a UID changeable card, a universal LFEN 4305. Now you can upload. So by buying the official real stuff, you can make your own magic changeable, UID changeable tag. It's kind of awesome if you like RFID nerds like me and Philippe. Yep. All right. So we did this, demonstrate some of this automated attacks of it, but we were not happy with that because it's interesting, but in the RFID field, there's loads of different card technologies. So if we was thinking a little bit about it, and Philip came up with the idea, how about we make a generic command instead? So we can try, instead of writing your own in automated attacks, which is kind of hard for the average person, but we make one simple when we implement it for hooks in several different technologies, like the 14A, 14B, the 15693s and iClass, and we combine it so we can do something called HV tear off. The HV tear off is a hook that we hook up when we say trigger at this point when I run this command afterwards. So we trigger this one first, enable it, and then next time you write that one, this will happen. It will trigger at a certain point. Very simple to run and do. And yeah,
we'll skip the...
If you don't want to, if you want to add your own commands for other card tech support, it's kind of easy to do. It's all open source, so...
Yeah, we'll skip this one, I think, because it's already...
What time do we have? Okay, shit. Okay, we skip this one then. Oh, shit.
Shit, as you say.
Shit.
Okay, then I go also pretty quickly on that one, just for you to get the principle of the attack behind. So we looked on the MIFARE Ultralight EV1, which is the up-to-date MIFARE Ultralight you can find on the market today. It's many security features. One of them is monotonic counter, which means you can always increase the counter, but you can never decrease it or even reset it to 0. So there are 3 monotonic counters, and you have some commands to play with, a command to increment the counter, a command to read out, and a special command to check if there was a tearing event, because actually there are several protections against tearing. Internally, that's something we found out by all our experiments. Actually, you have 2 different slots behind one single counter, a bit like for the EM4305, except that you don't see the slots yourself. It's just that the card decides which slot to show you when you want to read out the result. And you've also a validity flag. On the EM, it was one single bit, and the 8. Here, it's a full byte, and the full byte has to have a very specific value, 0xBD, to know that there was no tearing occur. If you tear, the BD wasn't written properly, and you can detect that there was a tearing event. In case of priority, so both are valid, then the card will compute which counter is the highest value, and it will return that one. So just be safe. So we have, I try to speed up, but I have to think what I'm saying.
It's not me.
So there are some examples here when you get like 1, 2, 3 plus 1 in normal condition. You get 1 to 4. If you can point at the same time I speak, it's easier. And if you want to check the tearing, you get the byte of the other slots, because if you interrupt something, that's when you were preparing the other slot. If you interrupt this 1, 2, 3 plus 1, what happens is that you get a corruption in the tearing flag, and it will send you back the other counter, which was not affected by the tearing. So to attack it, we need always to get this valid flag. So we tried first to do tearing at the very end of the write to make sure that at least the valid flag was written properly, and we played with that, and at some point we managed to get an old counter value, not the fresh one. So internally, what it means is that very probably a bit flip occur here, somewhere in the counter. So the validity flags are correct on both. So for the card, both slots are correct. And when it looks which one to show you, it sees that this one is smaller because one bit was not written yet. So it returns the old value. Based on that, what can we do as an attack? Let's try to get the counter to a power of 2. So we'll get one single bit in the counter. And if it can become weak, one single bit off to 0, all the counter is set to 0. So now what happens if you manage to get a weak bit on your power of 2? Two things can happen. If it's a 1, you will get the new value. If it becomes a 0, you don't get a counter reset to 0 because you get the old counter. We'll see later how we can put it back to all to 0. So now if the bit you're targeting on your power of 2 is not weak, because maybe it's written first and not later, that's not a problem. You just jump to the next power of 2 and you try if the next bit is weak. And you can scan all the bits one after each other, and maybe you're lucky, at least one of them will be written after the validity flag. So now how you get back to 0? We can play also with the distance to the reader, you remember, to enforce how a weak bit will be read. So once we get a situation when we are in an unstable read between two values in the reader, we can make it sure that it will be read as a 1, and we do a tearing earlier to corrupt on purpose the other slot. So now we will get one slot with a weak bit and another slot which is completely corrupted. So now when we read back that value, if the weak bit is seen as a 1, we have the counter, but if it's seen as a 0, then we manage to see a 0 in our counter with a validity flag. Still, it's a bit unstable situation, because sometimes you see the full counter, sometimes you see a 0. So how can you stabilize it? Put a card away from the reader, so the weak bit is more likely to be 0. And you do a plus 0. And when you increment the counter, you can also just say plus 0. So it will copy the one that is read as a 0 to a stable 0 on the second slot. And if you repeat the operation a second time, the second slot, will be copied to the first slot. And we end up in a situation when we have a very stable counter reset to 0 with a very stable valid flag. And we managed to reset completely the counter. And I'm afraid we are over something. Yeah. So no, come see us later if you want to have a nice demo on that. So there is a CVA, there is all family of tags which are affected on that. There are countermeasures explained on application note, at least mitigations, and there is no magic against that one. But for example, when you play with a counter, if you use a very high value counter, there is less chance that we can find this weak bit somewhere higher. So instead of counting from 0 to 10, you can count from FFFF something to FFF a bit higher, and it will be much harder to reset the counter. So that's it. That's over. That's our conclusion slide.
That's it. Yeah.
You got all the open source tools there to play with it. We showed just like fundamental technique to attack many different RFIDs or EEPROM, LF, HF, or even EEPROMs which are not on RFID. You may have also some luck on it, but you've always to target something where there is a security feature that you can activate, but you can't control the full result, and then maybe you will be lucky.
I think you just missed to say one thing on the last slide about the product family and why the resetting of OTP bits on those modern cards is that they are used everywhere in transport situation in the world all over the place. So yeah, it has implications. But then for other, we also wrote a paper for Stick. And so you have a tiny URL there to it. So
a nice long paper, very detailed.
Very much better explaining things than we are doing live, but we don't get live demonstrations. We open source those in the Proxmark repo. We also have one thing that happened during the COVID times. Instead of doing the old Proxmark forum, because it's kind of dead and boring, we started up a Discord server. So the RFID hacking by this man. We also got a vanity URL, so if you go to that one, you're most welcome to ask questions about everything about what we do. This is our Twitter handle, so with that said, goodbye, hug.